This is a video on flash memory, and it is narrated by me, Alfred Morabito. Flash memory is a type of EEPROM, electrically erasable programmable read-only memory, used in digital cameras, personal computers, audio players, industrial robots, video games, and a number of other applications. It has high mechanical shock resistance, withstands high pressure, temperature, and immersion in water. Flash memory is an exclusively electronic device in that it has no mechanical or moving parts. This allows less noisy interaction. Reads and writes electronically and does not need ultraviolet light to erase like other EEPROM devices. It was invented by Dr. Fujio Masuoka in 1980, was introduced to the market in 1984 by Toshiba, and flash memory was originally unsuccessful in the market until technical issues were solved. It became highly used in digital cameras and cellular devices in the 1990s. It was named flash because it is an erasing procedure which erases all the bit states in a flash. It has scaled in accordance with Moore's law considerably, with cell size decreasing from 36 micrometers squared in 1988 to 0.154 micrometers in 2003. The cost per megabyte also decreased from $1,000 in 1988 to 10 cents in 2004. And the cell size is scaled considerably more, reaching sizes of around 15 nanometers today. Flash is a type of non-volatile ROM read-only memory. Non-volatile memory retains the information stored on it even when its power source is turned off. Other types of non-volatile memory include other ROM read-only memory, ferroelectric RAM, hard disks, floppy disks, optical disks, and others. Flash memory and other non-volatile memory have a very large retention period compared to volatile memory such as DRAM. The retention period of flash today is around 10 years. A flash memory cell resembles a typical NPN MOSFET, but with additional floating gate underneath the control gate. Both these gates are typically made of a highly doped polysilicon. The floating gate is surrounded on all sides by an insulating oxide. The control gate is connected to other circuitry via a word line, and the drain connected via the bit line. These lines are connected to other flash memory cells in the device. This is an energy diagram of a typical flash memory cell. The floating gate is isolated on both sides by an oxide layer insulator. Electrons cannot travel across this barrier and reach the conduction band of the oxide with thermal energy alone. Electrons need a tunnel through the oxide to get to the floating gate underneath the presence of a strong electric field. Once these charges reach the floating gate, they will stay there even when the power source is turned off. Each cell can store information in the form of bits. A charged floating gate corresponds to a 0-bit state, while uncharged corresponds to a 1-bit state. Memory cells are erased in blocks at a time, which gives flash an advantage over other types of memory, which erase 1 bit at a time. Erasing removes all the charges from the floating gates, which sets all the bit states back to 1. There are two types of flash memory, NAND and NOR. NOR type flash was the original type of flash memory, and NOR memory has a capacity of around 1 to 16 megabytes, while NAND has a capacity of around 18 to 128 megabytes. NOR has a random access interface in that the read time is independent of where the information is stored in the device. NAND is accessed sequentially in that the location of the information to be read influences the read time. NOR memory is used to store code from smaller devices such as a digital camera, and NAND flash used more as a data storage such as a PC card. Programming. Charge can be stored in the floating gate of the cell in two primary ways: channel-hot electron injection and Fowler-Nordheim tunneling. NOR-type flash memory implements channel-hot electron injection in the program and uses FN tunneling to erase. NAND-type flash memory implements FN for both programming and erasing. In channel-hot electron injection, a large voltage such as 12 volts is applied to both the drain and control gate of the cell. The voltage at the control gate repels the positive charge in the P substrate and creates an inversion layer at the oxide semiconductor junction underneath the floating gate. An applied lateral electric field along the channel length of the inversion layer is large enough to give some of the electrons enough kinetic energy to tunnel through the energy barrier into the oxide towards the floating gate. These charges are then trapped there until an applied electric field removes them. As you can see, there's a high voltage at both the drain and floating gate, which allows the electrons to have enough energy to tunnel through the oxide. An electric field of around 0.1 megavolts per centimeter is usually required for this tunneling effect. In Fowler-Nordheim tunneling, a very large electric field of around 8 to 10 megavolts per centimeter is applied across the insulator. This process occurs at a slower rate than channel-hot electron injection, but can be more controlled. To erase the data in the cell, a larger negative electric field is applied to repel the electrons out of the oxide around the floating gate. This FN tunneling is used for both programming and erasing in NAND type flash, but only for erasing in NOR type. The trapped charge at the floating gate will screen or block voltage from the control gate. This, in effect, increases the threshold voltage to produce an inversion layer in the substrate that allows conduction. Cells in the program state will not conduct when an intermediate voltage level is applied, indicating that the cell is at bit state 0. As shown by the graphs, a program state will shift the threshold voltage to the right. Cells of flash memory are grouped together in square blocks. The rows of the blocks are referred to as word lines, and the columns of the blocks are called bit lines. There are two different structure of blocks, NAND and NOR type. The currents on the bit lines are dependent on the voltages at the word lines, and the bit lines are connected to other circuitry that can sense the output of the memory cells. In NOR type flash, the bit lines are connected to each individual drain terminals of each MOSFET. The word lines are connected to each control gate in this row. A source line connected to ground is also connected with the source terminal of each MOSFET. NOR flash is used to store less data than NAND, but is random access and faster to read. In NAND type flash, the bit lines are connected to strings of MOSFET transistors versus single ones. This is the reason behind NAND's serial address versus NOR's random access address. NAND type is usually used to store more data than NOR type. NAND type performs a role in data storage similar to that of hard disks. Flash memory is now being used more in the bulk of data storage in devices such as computers, specifically NAND type flash. Its advantages over hard disk memory is that flash has no moving parts and is highly durable compared to hard disks. The advantages of hard disks over flash memory is that the price per megabyte of data is still in favor of hard disks. Flash USB devices are more convenient than floppy disks and CDs due to their lighter weight and higher durability. Cutting-edge NAND flash today is manufactured using 15-nanometer processes. The scalability of flash has its limitations as the physics of the cell begin to break down as the cell becomes smaller and smaller. However, the market of flash continues to grow as the price goes down compared to hard disks, and its application continues to expand with the introduction of new technologies.